All right, so we're going to start functions of two or more variables. This is probably what you're going to mostly remember from Calc 3 is this chapter and then the ones that we do after. These other two are kind of background and they provide some framework and foundation for what we do next. But as far as the calculus of multivariable functions, here's where we're going to start. Okay, so just some basics here. F of x, that is just a function in terms of x, right? Sometimes you use y, but this is still really f of x, okay? Now, this is what you learned in Algebra 1. Eventually, you started using function notation for it and said, well, why have two different variables if really it's just one variable that is the input, which gives us a function in one variable. Okay, so that's what we mean by a function in one variable. In Calc 3, we're going to have, instead of y equals f of x, we're going to have z equals f of x comma y, which is now a function of two variables. Okay, you've seen these functions before. You probably just never wrote it this way. But for instance, if you think back to area equals half base height, this is a function in two variables. Okay, so you could have written it as f of b comma h equals half times base times height. Okay, so you've dealt with these before, you probably just haven't used the notation. Okay. We consider z the dependent variable. We consider these the independent variables. Okay. You could have functions that have more than two variables. So maybe w equals f of x, y, and z, and so on. Okay, in general, the restrictions of the independent variables determine the domain of f. So instead of looking at a function in just x, where we look at the right side and say, oh, well, here the domain is all real numbers, no big deal. Now if we have a function with x and y as our inputs, we have to look at both the x and y restrictions to kind of combine for a collective domain. Okay, same if we have more than two variables. Okay, so let's try a couple of examples here. Find the domain of the function f of xy equals natural log of xy. All right, what do you guys think? Yeah, Alex. Okay, it's a good start. So based on the restrictions of a log function, we know that the argument xy has to be greater than 0, right? So could we kind of group or describe like what coordinates could work? Yeah. When x and y are not 0 and have the same sign. Okay, that's perfect. Now let's put that into like a quadrant. Where are they the same sign? Let's just take what you said. First quadrant. There we go. Okay, so in this case, the domain is all ordered pairs in quadrants 1 and 3. Not on the axis. Okay. So you could either sketch the domain, you could describe the domain, you could write it all xy such that xy is greater than 0. There's lots of ways to describe it. Okay. Here's another one.
If it was L on XZ, or XYZ.
XYZ.
And do you write like all ordered pairs in cubes?
We'd say all ordered triples such that x, y, and z, or x times y times z is greater than 0. So that would mean out of the 8 octants that you have to pick from, right, as long as the product of the 3 is positive, that'd be kind of, I mean, you could sketch it, but it'd be a little bit convoluted to see. So that'd probably be better to just write it like that. That's a good question. Okay. So let's say we have f of x, y, z equals x over the square root of 9 minus x squared minus y squared minus z squared. Okay, so what restrictions can we start with here? Anything. I know you guys, some of you are working on it already.
X squared plus y squared plus z squared is less than or equal to 9.
X squared plus y squared plus z squared is, you said less than?
Yeah.
If it's equal to, that gives us 0, right? Because I'm assuming you started with this.
Yeah.
And technically we want that to be not equal to 0 because we can't divide by 0, right? Okay, so just, that's good. But, so this would be the domain. How can we describe this? So set of all ordered triples inside a sphere with what radius? Yep. Centered at the origin, not just any sphere. Good. Okay. And staying with the same function, what's f of 2, 1, 1 going to be? How do we find that? Yeah, just like before. If you have f of x and you're finding f of 2, you plug 2 in for x. Here you have f of 2, 1, 1, so you plug 2, 1, and 1 in for x and then y and z respectively. So plug those in, we get 2 over 9 minus 4 minus 1 minus 1 is going to be 3, isn't it? Okay, pretty straightforward stuff so far, right? Any questions? As far as graphs are concerned, z equals f of xy is a surface in 3 dimensions. We've already talked about most of these. So, for instance, if f of xy equals a square root of 4 minus x squared minus y squared, a great way to think back to the shapes that we talked about graphing is to consider this as what variable here? Z. And if it still doesn't look familiar, manipulate it, try to get it to look like something that we've seen before. Maybe you square both sides. And if we move some stuff around, look familiar yet? What is this? It's a sphere. However, taking a look at the original function, right? We know that f of x, y, or z has to be greater or equal to 0 by default, right? So it's not the whole sphere, it's actually just going to be a hemisphere, the top half, right? So okay. Not that you have to do all this, but you get the idea. Hemisphere only, since z was greater or equal to 0. Okay? Okay. We're actually almost done here. Let's talk about level curves and contour plots. Okay. So let's say we have some surface z equals f of x, y. And we take a plane at z equals k, and we slice through the surface. Okay. If we graph the resulting figure, okay, this is called a level curve. Okay, so if you imagine any three-dimensional surface and just slice through it, okay, the curve that you get as a result, that's what we mean by level curve. Okay, so I mean, we could actually talk about several of these right now. If we took, so here are some examples. Let's say we have z equals x squared plus y squared. What's this surface look like again? What's it called? Elliptic paraboloid? Sure. Hopefully you just know it looks something like that, right? If we took planes and cut through it, z equals 1, 2, 3, 4, and so on, what level curves are we going to have? Circles. Very good. Okay. So okay, so here we have a set of level curves. Okay. Each one corresponds to a z value. I like to think of that as height. Okay, so for instance, this first level curve, that might be when z equals 1. This next one might be when z equals 4, right? The one after that might be a little bit higher, and so on and so forth. Okay, so maybe this was z equals 16, and so on. Okay. Now, if we take a set of level curves and sketch them, that's what we call a contour plot. Okay, so meaning if you have a flat piece of paper like the one I'm using, and I gave you something that looked like this, you should be able to gather some information like, you know, if you were stranded here at this location and you start moving this way, what's going to happen to your height? It's going to increase. If you go back the other way, you're going to be going downhill, right? So from a contour plot, you should be able to get a gauge as far as whether you're going to be increasing if you go a certain direction, or if you're going to be decreasing if you go a certain direction. Okay? Why don't you guys try sketching this contour plot? So let's say f of xy equals x squared minus 4y squared. Okay, so take a couple minutes, pick some nice values, and see if you can get a decent sketch for a contour plot. And then I'll show you what I have. So to... Oh my god, I left Sean and Sajani out in the hallway this whole time. I am so sorry. I totally did. I'm like looking around, and I'm like, I feel like something's not right. No one's saying anything. I am very sorry. I haven't done that since like my second year teaching. Last time I did that, the person was taking a nap on his backpack in the hallway. But the good news is that what we're doing is not very difficult. And it's being recorded. I'm very sorry. Okay. So, for a good contour plot here, I just kind of picked 0 to start. Kind of solved, so I get 4y squared equals x squared, which then translates to y equals plus or minus 1/2 x. So this is where z equals 0. And then for z equals 4, if you divide by 4, you get a hyperbola. Okay? It opens in the x direction. We're going to go out 2 for the vertices. We're going to have something like that. So this is where z equals 4. If I do negative 4, it's pretty much the same story, just along the y-axis. Now we're going to open in the y direction. Vertices will be 1 unit away from 0, 0. So something like this. Okay, so this is a decent sketch. Pretty much tells you where things are happening. So if you didn't know what shape this was, you should be able to figure it out. If you're stranded at the origin and you move in the positive x direction, so this way, what's going to happen to your height? Well, what's the current height here at the origin? What does z equal here? 0. If I go right, what's going to happen to the z values? It's going to increase. What if I go left? So if I go right or left, I go up in height. If I go up or down, decrease in height. Think three-dimensionally now. If I go forward or backwards, I go up. If I go side to side, I go down. What shape is that? That's the hyperbolic paraboloid, right? So we can, from a contour plot, we could also get a gauge for what the function is, even if we don't know what the function is to start. Okay? So that's for contour plots and level curves. There is something called level surfaces. Okay, and the analogy here is that if we have 2 variables, graphs are surfaces, we can project as level curves. When we have 3 variables, Now we have a 4-dimensional graph, which we're going to get really good at graphing. Just kidding. But now, instead of level curves, we can project as level surfaces. Okay. So with 2 variables, we have a 3-dimensional surface. We can project onto 2D and get a feel for what's going on with the function. Okay. With 3 variables, we have a 4-dimensional graph. We can't really graph those, but if we project, we can get a feel for what's going on with the function itself, depending on what position we're at in a 3D system. Yes? Just from this contour plot? So, if we're here, see where we're at, what line does this correspond to? Corresponds to z equals 0. Does that make sense? So anywhere on this height, or anywhere on this line rather, we're at a height of 0. So if I instead have said, you know what if I go along this line? Well, then you're not going to really change your height at all. You're going to stay at 0 for the height, right? But now if we go this direction, even though I don't have every single level curve there, we get a feel that since we're going up to z equals 4, that if I were to travel in that direction, I have to go up to get there. Because this green curve corresponds to z equals 4 as a height. Does that make sense? Okay. So real quick, let's say we have f of x, y, z equals x squared plus y squared plus z squared. And I want to know, or I want you to describe, I can't write today. Describe the level surfaces. Okay, and I mean, you hopefully are getting to a point where to find a level surface, all we're doing is what on this side? Plugging in some values, yeah. So if you plug in something like 1, right? What do we get? A sphere. If I plug in 4, another sphere, right? I can't have really any negative values, okay? So in general, we can say that the level surfaces are spheres centered at the origin. And in general, as your position, as your distance from the origin increases, okay, so is your other value. Okay? So that's pretty much this section in a nutshell. I wanted to show you one picture real quick.